EDX Core Pure, Matrices 2, Transformations and Invariants, Rotations in 2 dimensions. What transformation does this matrix represent? We're going to apply it to the given object. So we're going to multiply 0, 1, minus 1, 0 by the coordinates of the 3 vertices. So I can do the multiplication now to find out what the image will be. So multiplying the top row of the first matrix by each of the columns of the second matrix would give me minus 2, minus 2, minus 4. Then multiplying the bottom row of the first matrix by each of the columns of the second matrix would give me 1, 5, 5, and that would be the image. So there's the image. So the point A is mapped to A dash B to B dash C to C dashed, and this matrix represents an anti-clockwise rotation of 90 degrees about the origin. If we start off with the identity matrix 1, 0, 0, 1, remember the first column represents the direction of the thumb, and the second column is the direction of the index finger. To create a 90 degree anti-clockwise rotation, so we're going to rotate our hand now. So there's the hand rotating anti-clockwise. The index finger is now pointing at minus 1, 0. The thumb is pointing at 0, 1. Remember, the thumb direction always gives you the first column of your matrix, and the index direction gives you the second column of your matrix. So the 90 degree rotation matrix is 0, 1, minus 1, 0. The first column is represents the thumb direction, and the second column represents the index finger direction. So all we need to do is to find out what will happen to 1, 0, which is the thumb, and 0, 1, which is the index finger. So example 1. Can we find the transformation matrix for an anti-clockwise rotation of 135 degrees about the origin? So we're going to do this geometrically and then see it done using a formula. So we're going to take 1, 0 and 0, 1, our thumb and index finger, and we want to create a 135 degree rotation about the origin. So the geometry here. So that red line is still 1 unit long, and this one is 1 unit long. If we just add a little bit more information here, that's 90 degrees, so the rest of this rotation must be 45 degrees. If we do a little bit of trigonometry, we know the hypotenuse is 1 and the angle is 45, so this length is root 2 over 2, and this length is root 2 over 2. Similarly, if we just add a little bit of geometry onto this diagram, we know that this angle is 45 degrees due to the 135 degree rotation, and a bit of trigonometry gives me this is root 2 over 2 in length, and this one is root 2 over 2 as well. So if we remember, the direction of the thumb will always give you the first column of your transformation matrix. So if we look at this one first, which way is that pointing? It is pointing in the direction minus root 2 over 2, root 2 over 2. And if you look at where the index finger would have ended up pointing, which is this one here, its coordinates are minus root 2 over 2 and minus root 2 over 2. So there's a neater version to show exactly what's happened. So the 135-degree rotation anti-clockwise about the origin, you could take the root 2 over 2 out as a common factor, and that would be your rotation matrix. So these are the rotation matrices we need to be aware of. So the first rotation matrix is 90 degrees about the origin anti-clockwise. The second rotation matrix is minus 90 degrees about the origin clockwise. The third rotation matrix is 180 degrees about the origin. Clockwise or anti-clockwise would give the same direction. And the last one is a rotation of theta degrees about the origin. Be careful with the last one. Clockwise rotations are considered to be a negative angle. You can try using GeoGebra again to investigate the significance of what happens to the points 1, 0, 0, 1 and their images using the link provided. In the next session, we're going to be looking at stretches and enlargements in 2 dimensions.